I also need my notes since it's a bit more involved. Okay, so we are going to be generalizing what we did before by talking about Dirichlet L series. We call them L of a variable s and a function chi, where this is the characteristic characteristic. Sorry, I can't spell today. This is the Dirichlet characteristic, and we're going to be generalizing the zeta function, basically writing it as a sum from n equals 1 to infinity of the characteristic divided by n to the s. And we need to talk about a Euler product version of this. Well, you can also do the Euler product on this using a much more complicated sieving argument, which I can't really prove myself, so I'm not gonna show you guys. We can represent this as the product of all the primes as well, what looks similar to what we had before, but with the characteristic function instead of 1. So recall with the zeta function, this was just equal to 1, so the zeta function in some sense is the simplest L function. Let's talk about a specific example of the L function. Because what the hell is this thing? What is it? Okay. Example one that we need is the beta function, which is defined to be sum from n equals 0 to infinity of -1 to the n. Okay, we're getting pretty interesting here. Over 2n plus 1 to the s, which we can just write as, well, we got 1. Now we have the odd numbers on the bottom. Minus 3 to the s plus 1 over 5 to the s minus 1 over 7 to the s, and this continues on indefinitely. So we basically took some terms that we had from the zeta function and changed some signs. And that's all the L functions really mean. They aren't really that scary. It just allows you to do more things than you could before with the zeta function. And now to write it in this form, you see we have to find a characteristic function that gets rid of the minus signs. Basically, we want to get rid of the -1 to the n over there. And I should also write a condition for this. We need to have chi multiplicative. So chi mn is equal to chi m of chi n. This means that chi is multiplicative, which is a pretty easy condition to satisfy since it'll involve primes and so forth typically. All right, let's get started. So we're going to write this. So now as we're going to break it up into the odd and even terms. Sum as n goes to infinity of n even minus, since we see all the odd terms in this series have a minus sign, sum with n being odd of 1 over 2n plus 1 to the s. And we can further break this up into the following sum, indexed set by k now. We have, well, definition of even, we're going to have something be equal to 2k. Definition of n being odd, we're going to have it be equal to 2k plus 1. So we're just going to substitute that into these expressions here. Just going to be, going to need more parentheses, of 1 over 2 to the 2k plus 1. These are the even terms to the s power minus 1 over 2 to the 2k plus 1 to the s power. Fantastic. And now we can multiply these out. We just recognize it as being equal to sum k equals 0 to infinity of 1 over 4k plus 1 to the s power minus 1 over 4k plus 3 to the s power. And it might not look it, but we have made some progress. So this tells you that the beta function is actually equal to, so from n equals 1 to infinity of chi to the n over n to the s, the form we want for chi of n equal to the following function. We have 1 if n is equal to 4k plus 1, minus 1, n is equal to 4k plus 3, and 0 for all other cases, including all evens. And yep, that's basically all we need. We can now write down our final expression. Running out of room though. I'm sorry if this seems a bit involved. The Wikipedia article did not actually prove this relationship for the beta function. I wanted to prove it, so I do apologize if there are slight gaps in my reasoning or if it seems a bit contrived. Okay, so now we can write down beta of s is equal to, let's just write down the complete expression. N equals 0 to infinity minus 1 to the n over 2n plus 1 to the s. And now we write it as the Euler product. I'm going to have two products this time, a bit more complicated than the previous one. We have forms of primes. Products of primes is the form 4k plus 1, 1 over 1 minus 1 over p to the s. We have another product of primes equal to the form 4k plus 3, 1 over 1 plus 1 over p to the s. This seems cool. What we're going to do now is basically what we did before with the zeta function. We're going to set s equal to 1, see what we can find out. Should be pretty interesting. All right, what happens if we set s equal to 1? Well, if we do that, for s equals 1, then we have beta of 1, which is sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1, which we can write out as 1 minus 1/3 plus 1/5 minus 1/7 plus etc. And on the other side, which we can write as the, this is the Leibnitz series. For pi over 4, very famous result. So many YouTube videos about it. I don't need to go over it again. On the other side, we can talk about the primes. So we're going to have it equal to as well. Product of p equals 4k plus 1. 1 over 1 minus 1 over p. Product of p equals 4k plus 3. 1 over 1 plus 1 over p. Which we can write by multiplying top and bottom by p. And that's going to be product p over p minus 1. Another product p over p plus 1. And when I write this out, what you can do for yourself, first term starts from here. We plug in 0 for k, we get 3. This is 3 over 4. Next term comes from here. I'm writing so small today. 3 over 4. Next term comes from here. Plug in 0. We get, no, that's not good. Plug in 1. We get 5 over 4. And we continue this on for a while to get 7 over 8, 11 over 12, 13 over 12, 17 over 16, 19 over 20, etc. As you can see, it has something to do with the nearest multiple of 4, which you can write in that form as well. So we have something similar here to the previous one. We have pi over 4 being equal to this series, which is equal to this product. Now we don't want to talk about this converging, but we want to talk about this being rational. So just an aside here. So we have our double product is rational. This tells us that our sum must be rational as well, but the sum is equal to pi over 4. So this tells us that pi must be rational. No, I don't want to confuse you by writing pi. The double product tells us that pi is rational, which is obviously a contradiction. Right. So in order to show that the product was rational, we did by way of contradiction again. Set of primes is finite. This tells us that, yeah. So if there are only finitely many primes, then this does converge, and in particular, it's rational. If that happens, then pi must be rational, which is obviously a contradiction, since pi is irrational, as everybody knows. And we are done. Thanks so much for sticking with me. This proof was a bit involved. If you actually wanted to show the beta function relationship, if you go on Wikipedia, it only shows the numbers here and the product equal to the sum here. I wanted to flesh out a bit more detail so I could be sure I fully understood it. And those are all of the proofs of the infinitude of the primes that I know. If you have more and you want to see them on this channel, feel free to comment. I'll see what I can do. There are also a few others on Wikipedia that I couldn't get to, so maybe I'll get to them in the future. If you want to see more, feel free to subscribe. I'll be seeing you next time.